Hello everyone. We are going to discuss today one of the complex topic of our digital system design subject. That is one of the subject of third semester in BTech electronics engineering. That is analog to digital and then digital to analog converters. And how we can convert a digital signal into analog signal, and how we are going to convert the analog signal into digital signal, and the circuit that involved in doing these kind of converters. So first of all, there is some specification that must be fulfilled before the conversion processing has to be started. Like in case of digital to analog converters, we have to involve some we have to fix some specification for each digital to analog converter that is the minimum requirement that a particular converter must have to fulfill. So the first one is the resolution of the converter. So how much amount of digital data that is going to be how much amount of output analog voltage that is going to be changed when a single digit or the least significant bit is in the digital input is going to be changed. So that is known as the resolution of the digital to analog converter. So if we can see the formula, that the full scale reading, that the output full scale analog reading, that is divided by 2 to the power n minus 1, where n is the number of the bits in the digital input. So, or we can say this is the this is the least significant bit increment in the voltage at the output. So the full scale reading for, let's suppose we have a converter of 8-bit digital input. So for 8-bit digital input, the resolution is 0.392%. So let's suppose the full scale reading is 1, or we can say 100. So if we take this this full scale reading of 100, and if we divide this 100 by 255, which is nothing but 2 to the power n minus 1, that 2 to the power 8 minus 1. So we have a scale reading of 0.392 of the 100 volt scale. So if we convert into the percentage, so it became 0.392%. So if we can say that there is a change in the input voltage of 0.392 volts if the scale is of 10 volt, and or we can say in millivolts it is 39.2 millivolts. So this is the minimum change in the output of the digital to analog converter when a single digital input is changed, only significant bit is changed. Next is the accuracy. Accuracy is the maximum deviation of the actual value to the ideal value of the converter. Let's suppose in the mathematics we have some value that after the conversion we have to get this value, but in actual converter it can shift by a little error. So that accuracy, if the maximum amount of error is actually the accuracy. If this maximum amount of deviation is very small, then the accuracy is very high, and if the deviation is very low, then the accuracy is not that high. Next is the conversion time. That is the time amount that a converter can take after the digital input to produce an analog output, and that is known as the conversion time. And the speed of the converter is decided by this conversion time parameters only. Next, the settling time. After the providing of the input, that's the amount of the time that is taken by the converter to settle within a particular error limit is known as the settling time. So if we can see the graph, when the input is applied, there is a this is the expected input, and there is a initially this is the time scale, and there is a jump, as we can see, over the actual value, and then goes down and then up and down, and then it became settled within a particular limit of plus 1 by 2 LSB to minus 1 by 2 LSB, and this is actually the settling time. So that amount of time must be required to settle the input provided by the to the digital to analog converter to produce an output. So this is one of the part of the actual conversion time, the settling time. Next is the stability. Stability is nothing but to produce a stable output again and again. If we change the time, if we change the temperature, if we change the power value or fluctuation in the power level, so there must be, the output must be stable. It can produce the output that is predefined, or we can say that is expected. So if it is a very high stable digital to analog converter, it can be free with the drift in the temperature, drift in the power supply voltage, or aging effects. So how a digital to analog converter work? There are basically two type of digital to analog converters: binary weighted register digital to analog converter and R to R ladder converter. So in the first case, this is a operational amplifier, as we can see over here, and this operational amplifier is working nothing but as a summer. The different voltages are going to be summed due to this summing. This is on this point due to this summing property of the operational amplifier. Now what we have to provide? We have to provide the digital input to the different switches in this array of the resistance. The first resistance having the value 2 to the power 0 R, the second is 2 to the power 1 R, 2 to the power 2 R, and the last resistance, if it is of n bit, that is 2 to the power n into R. So due to this varying weight of the resistance, the amount of the voltage is again going to be divided as the number of the bits, as the number of the bit increases from 1 to n. So whatever the bit is exists, like this is from 1 to n, and we have the input like this. So if 1 is exist, the switch must be closed close to this value. If 0 is not exist, it must be grounded. For the third case, it must be again grounded, and for the fourth case, it again grounded, and for fifth case, it is again connected to the summing amplifier. So and this is the reference voltage that is provided to this converter. So if we can say that the amount of number of ones and the position of number of ones is actually going to be sum up over here and produce a particular output at the output terminal. So this is the amount of the current that is entering, and this current is nothing but V reference voltage divided by R, the weight of the resistance, multiplied by bit V1, then V reference upon 2R into B2, and this goes to V reference 2 to the power n minus 1 R into Bn, or we can convert this value into the voltage by nothing but V naught is equal to minus of I naught into R, which is RF, which is the resistance used in the feedback path, which is nothing but the one of the multiplier of R itself. So we can in this way we can produce the digital we can produce the analog output for the digital input 1 with the help of digital to analog converter weighted resistance type. The problem with this converter is that the value of the resistance is going to be changed and going to be doubled every time. So if the value of n is very large, there is a varieties of resistance required which can take a different spaces on the IC over which we are going to be implement this circuit. So the small resistance taking a very small space, while 2 to the power n minus 1th resistance take a very large space on the IC. So the variable space occupied by the different resistance and occupied by, and again the amount of the space that is again large, this converter, this generally changed by R to R ladder due to the variation in the resistance values. The next is binary R to R ladder, in which there is two type of resistance is only used, either R or 2R, and there is a network of R to R in the form of ladder. That's why it is known as R to R ladder and digital to analog converter. The process is almost same. For the bit that is exist, that is equal to 1, the switch is connected to the summing of the amplifier, summer amplifier, and if it is 0, it is connected to the ground. Same amount of current, this is the V reference voltage, and the amount of current is going to be collect over this line and this is summed up by this summing amplifier and produce the voltage output. The voltage output equation in this case is given by VR. This RF is nothing but the feedback resistance, RF by R into V reference, and this is the equation of the number of bit that is going to be entered. So if D0 is the least significant bit and Dn minus 1 is the most significant bit, the equation is D0 into 2 to the power 0 plus D1 into 2 to the power 1 up to Dn minus 1 into 2 to the power n minus 1 divided by 2 to the power n. So in this way, it can produce the output voltage for the different digital input data. So these are the two converter that is frequently used in this subject for converting the digital input signal to analog output. Now these are the analog to digital converter. Now this time we are going to produce the digital output for the analog input signal or analog input voltage. So these are the classification of different converting process, how an analog signal is converted into digital. The first is integrating type digital to analog converter. In this category, we have two, a single slope and a dual slope integrating type analog to digital converter. In these converter, the accuracy is very high, but the speed is very slow because it takes multiple 2 to the power n cycle to convert the signal, to convert the analog signal into digital one. The next is successive approximation type analog to digital converter. In this case, the accuracy is medium and the speed is again medium. So it is a compromise between the speed and accuracy, so that we can get an digital output for the analog input in a proper time with certain amount of accuracy. While in case the third one is the first, that is flash type converter. In this case, the accuracy is very low, but the speed is very high. So we can also manage to increase the accuracy by increasing the complexity of the existing circuit, but it take a lot of cost as well as a lot of space on the IC. So we generally use this flash type converters where the accuracy is not required so much, while the speed is one of the judgment parameters. So basic principle how we convert the analog signal into digital one, and this is one of the requirement or prerequisite to understand the concept of analog to digital converter. The first one is the analog input signal, which is nothing but the signal varying in time with its amplitude. Amplitude must be a voltage or a current value. Now with the help of sampling and hold circuit, we can sample this continuous time axis into different discrete time data. As we can see over here, it must become constant between this gap, but it can change over this particular time instant from here to here, and then constant with this gap, and then again constant with this gap. So it's the change which is continuous over here at a particular time. There must be a data while in after the sampling and hold process, there is a certain time over which the data exists or data is going to be changed. Either it became constant between the two time period. So now this time we can say that the time axis became discrete, but the amplitude axis is still having the data at every point, or we can say it is a continuous. Now with the help of quantization and encoding method, we can now quantize or discrete the analog amplitude value as well. With the help of quantization processing, and then after this we provide a different code to each level, so that it can be encoded and it can be easily stored or supplied or converted into the digital signal. So this is actual circuit that is used to convert the analog signal into the samples of the signal by using sample and hold circuit. So analog signal is applied over here, and there is a clock pulse that is provided at the gate of this MOSFET transistor. So whenever the gate having the pulse, the amount of voltage is going to be passed, and it can charge this capacitor to positive and negative value by the amount of the amplitude that is exist at that time. So it became charged. For the next sample, it became discharged up to this point, from this point to this point, by a current flowing into this operational amplifier. Or if the voltage is increased, it can increase the voltage by current flowing in this direction. So in this way, by providing different clock pulse, that the clock pulse is like this, we can sample the input data with the help of this sample and hold circuit. Next, after the sampling and hold process, the sampling must be at a uniform interval, taking sample from each location, and this is nothing but the digital approximation of the analog signal. So this is nothing but the description about sampling and hold, as we already discussed. And now the process is quantizing. Like in case of quantizing, the amplitude axis must be described by different level. Let's suppose we have k level, where k is nothing but 2 to the power n. So if we want to convert the data into digital one having n number of bits, so the number of level must be 2 to the power n. Like let's suppose we need the output for the analog input that must be of 8 bit, then this n is became 8. So the total number of level is 2 to the power 8, that is 256 level in which an analog axis is divided. So then there is a quantization size or quantization error. So this is the quantization step size. We can say represented by Q, which is the maximum value of the scale minus the minimum value of the scale divided by total number of samples. So this is nothing but the resolution or step size of the quantizer, or we can also predict the quantization error, which is nothing but the Q divided by 2, that is the quantization error. And then after this quantization, each level is encoding with the help of encoder circuit. So this is the process of how quantization and encoding works. So in case of over here, so if this is V minimum and this is V maximum, so we have the quantization size is equal to V maximum minus V minimum divided by total number of level is 2 to the power 3. Where in this case the code size is of 3 bit. So this is the quantization level, that is the gap between one level to the another level. So if we approximate a particular signal, let's suppose the sample size is this. So if we approximate, we either increase the level by maximum of Q by 2 or decrease the level by maximum of Q by 2. So the maximum amount of either increase or decrease to approximate the value for a particular sample, it must be, that is Q by 2. So we can say that the quantization error must be maximum value must be Q by 2. It may be less than Q by 2, but not greater than Q by 2 in any case. So after the quantization process, after the quantize each signal to a particular level, each level is provided by a code. Let's suppose for this level we have a code 000. For this level we have a code 001, 00010, 011, and in this way we can provide the different code to the different level. Now we have to transmit this code only, not a particular signal, but to transfer this code only, or we can save this code only to produce the analog digital equivalent of the analog input signal. So in this way, sampling, quantization and encoding combined produce a analog input for the digital input for the analog output, digital output for the analog input. Now this is some point where that is Nyquist state, that is sampling must be greater than twice the signal maximum frequency. If this is not happened, then in this case we do not recover the signal. We can convert the signal into digital, but cannot recover or convert digital signal to the analog one again, having the very large amount of error known as aliasing. and this is quantization error, as we all already discussed. And again, there is some specification of analog to digital converter, that is resolution. In this case, it is opposite of the previous one, that is the amount of the required minimum input voltage, analog voltage, so that it can produce the 1 LSB change in the output. So it is again V full scale value upon 2 to the power n. It is not 2n, it is 2 to the power n minus 1. So we can find out these values again, the minimum voltage that is required to produce a 1 LSB output. Quantization error we already discussed, it must be of the maximum of plus minus half of LSB. So we can easily calculate this. Now conversion time, again the time required for the digital, for the input of analog signal to produce a digital output. Analog error is error occurred due to the variation in the DC switching point of the comparator, resistor, reference voltage source, ripples, noise introduced by the circuit. So this is the analog. If you are going to input an analog signal, there must be an analog variations. It must be ripple, voltage source variation, or resistance value fluctuation, due to which a analog input signal can have some noise, can have some errors. So it can include in the digital output. So first of all, we have to remove this analog errors. Linearity error is nothing but if the step size that we are going to be fixed at the time of quantization is varying by some way. Now for let's suppose for one case it is very small, for the another case it is very large. So the step size is varying, then this became a non-linear quantization, and due to this non-linear quantization, the linearity error is introduced. We can also take the advantage of this non-linear quantization if the signal is varying very fast. This is called adaptive quantization method, which we are not going to be discussed over here. But there is linearity, that step size must be constant. So this is one of the integrating type analog to digital scheme, where we can discuss the dual slope. We will discuss the single slope in the upcoming slide as well. So in this case, we have an integrator which get an input from the input signal voltage, and it integrate the constant input voltage in with the help of integrator. So in case of integration, if we have the constant, it will convert it into a slope or a line. So this integrator convert this constant voltage into a slope. The amount of the slope is defined by the value of the constant. If the constant value is high or the input voltage is high, the slope is large. The input voltage is low, the slope is low, and we can produce this output or integrate it for a constant value of constant time. After this, we have a comparator that can compare the value with the zero voltage, and it can also provide a signal to the control logic to start a particular count. Now, how it can convert into the digital count, we can see over here. This is the input reference voltage, and this is the load, and this is the T load time, that is time required to load the signal. Like over here, if the voltage is low, then the slope is low, but for constant time T load. For the high voltage, the slope is high, and for next higher voltage, the slope is again high, but the time is constant. But in the next cycle, what we do, we became constant the slope. How we can constant the slope? We can provide a fixed V reference voltage. The switch is now V reference at the V reference point this time. So the voltage is known and it is fixed and it is having negative value, so that the slope must not going to be increased, and this time is going to be decrease the slope. So in this case, the same process is followed. The thing is that in this case, the slope became constant, so the time became variable. So the amount of the counter run is depend on these values of time. So if the voltage is low, the amount taken to to reach the zero value again is very less, and the counter run for a small time, and it can produce a smaller digital output, while the amount of the time is large. For the large input voltage, the digital counter run larger time and produce the digital output again, which is larger than the previous one but smaller than the higher one. So in this way, your digital to analog converter for the dual slope can work. The advantage is that taking low area, simple structure. The disadvantage is it is slow because it takes 2 to the power n cycle. The time interval is again not constant because it can produce the output for take a longer time to produce a output which having the large input values. Next is the successive approximation. It have the medium speed and medium time. This is again we have a comparator over here, and there is a DAC required in this successive approximation. ADC, we need a DAC required, and this is one of the disadvantage of this successive approximation register. So in this case, what we have to what this circuit do, an input voltage is integrated and provided to the logic circuit. So if the integrated is compared, not integrated but compared. So if the compared value is greater than the initial 0 value, it can set the most significant bit to 1 and rest of the bit to 0, and it provide the data to the DAC, which can produce the output, analog output, which is equivalent to 1 0 0 0 0. Again it compare the value with this new data, and if it is again 1, then it can going to set the next bit. And in this case, for the n bit output, n number of cycle required to set all the bits. If the comparator output is low, then that bit became 0, or in the case of initial one, it must become 0 if it is lesser than the previous one. So in this way, we can set the digital output, and this digital output can be displayed on a digital screen of the comparator. So its speed is a little higher because in the previous case we need 2 to the power n cycle. In this case, we need only n cycle to produce the digital output, but the accuracy is little less. So this is the configuration in which we can see how the DAC work. Input data is compared. This is the successive approximation register where one bit is most significant bit is set first, then again second and first, and it is compared with DAC. So this is the actual diagram where thing is going on, like V reference divided by 2 over here, and in this way. So this is the chart how we can provide 101 values. Next is flash type. In this case, a digital comparator is used for the input values, and it can compare with the reference values and provide the digital output with the help of encoder circuit. This is very fast. Then is counting type, and this is all for analog to digital converter and digital to analog converter for the digital circuit. Thank you.